Okay, hi everyone. Welcome to this week's seminar from our Wolfram Technology webinar series. The topic for this talk is time series processing in Mathematica. What is the agenda for this talk? Let me just blow up this a little bit, so I think it's better. We'll just we'll do a general introduction into the problem field of time series processing. Since time series processing, of course, deals with dates and times, we'll review how dates and times are handled in the Wolfram language. Then we will look at the features that the Wolfram language provides for representing the time series data in Mathematica. And then we'll have a look at the kind of computation we can do with time series data in Mathematica or in the Wolfram language. What is time series processing about? Time series is defined as a series of data points indexed in time order. This is a very interesting field because time series data arises in any domain of applied science and engineering which involves temporal measurements. And since measurements are so common nowadays, most of the data we deal with now is actually exists in the form of time series data. For example, in finance, you have market data, which is created every day, like for example, stock courses and interest rates. These are all quoted every day in various different places on the world. And of course, we have if you take this data over a certain period of time, you get a time series. In econometrics, for example, we have econometric figures like, for example, the GDP output of a nation or a certain region, which of course also has a seasonality and therefore can be considered as a time series. Then we have, for example, weather forecasting, where we have many different weather stations around the world, which always measure things like temperature or air pressure, and thus create a very long-running time series, which can then be exploited for doing weather forecasting. And of course, a not so good fact is, of course, surveillance. The devices we carry with us, the smartphones, the smartwatches we carry, they record every movement we make. And of course, if you associate this data with certain time, you also get time series data. Time series data have, by the way they are created, they have a natural one-way ordering. And what can we actually do with time series data? There are two different fields. The first one is called time series analysis. Time series analysis analyzes time series data in order to extract meaningful characteristics of the data. Like, for example, some really interesting figures, like, for example, the mean temperature over a certain period of time, or other statistical measures. And of course, in this time series analysis, we assume that the current values will be expressed as deriving in some way from past values. This is also a very important aspect of time series, as we don't consider future values having an input on current values. We only assume that current values are expressed as a result of applying some kind of transformation to past values. Of course, there's also time series forecasting, where we try to extract a model from our time series data and use this model to predict the future values based on previously observed values. This is also a very a field where a lot of research is currently going on. And in software architecture, there's an interesting trend where all data models are replaced with so-called event-driven data models. That means instead of recording the state of a system at a certain point of time, what software nowadays actually does, it records the events. Like, for example, if you order something from Amazon, Amazon records when you put something into your basket. When you when you do a checkout with this basket, it records that an invoice needs to be created and all these things, so that you get a history over time. And the actual state of some point in time is derived by applying, doing a replay on all the events, so that you can really always replay and look back in the history of certain systems. For Wolfram and Mathematica, this means that any kind of data you are going to import will most likely nowadays be in the form of time series. How do we do time series processing in Mathematica? Mathematica has time series processing built in since Math version 10. That means time series are first-class objects. Times can be absolute values or calendar time. Sampling can be regular or irregular. Sampling means that when the times, intervals when you make a measurement, these can be irregular or regular. Time series values can, of course, be scalars or vectors, depending on the kind of data that you are recording. Time series values can be single-variate or multivariate. This also depends on the field where this time series is valid for. It has Mathematica has a concept of missing data in time series, where missing data can be interpolated from surrounding data. And it has a lot of built-in tools in the Wolfram language. Like, for example, you can do transformations on time series data. You can do descriptive statistics. You can apply filters. Of course, you can do visualizations. You can derive models from the data, and you can do automatic forecasting from these models then. Before we, of course, let's just review how date and times are handled in the Wolfram language before we talk about time series. The first function that Mathematica had for dealing with time was the function absolute time. Absolute time was added in Mathematica 2, and it just gives the total number of seconds elapsed since the beginning of January 1st, 1900 in the local time zone. This is very important. For example, if I run the absolute time function, you see this is the number of seconds elapsed since January 1st, 1900. And the important thing is that this figure is with respect to the local time zone, which is given using the $time zone variable on my machine. It's +2 because I'm actually located near Vienna, and here we have currently the central European summertime, which has an UTC offset of 2. And if, for example, I used to calculate the absolute time value at January 1st, 1900, the value is, of course, 0. If I use a different time zone, for example, like UTC, you see that it actually returns a negative value because, as I mentioned, the value in absolute time always is with respect to my local time zone. And since UTC has an offset of 2, the actual value is minus 7,200. And of course, there's another interesting figure, which is called a time unit. Time unit gives you the accuracy of the clock which absolute time uses. In Mathematica 6, another important information function was added, which is called date list. Date list produces the current date in the form year, month, day, hour, minute, and second. And of course, I can also give an explicit date to date list in the form of a list. And what date list then does, it fills up the remaining information by the zero padding the list. And again, when you use a different time zone, the result is always shifted to the local time zone. Like, for example, using date list with a time zone of UTC, you see that actually for example, in Greenwich, actually the current time is 1:30. Let's just give the other function that Mathematica 6 introduced was date string. Date string returns the date as a string representation, and here I can use by using the argument. I can, for example, apply different formats. Like, for example, here this is a more comprehensive format, and here this is ISO date, gives the current date in ISO format. And I can also use the ISO date time in times on UTC to produce a real ISO time stamp, which is very important when interfacing with other software nowadays. Of course, the drawback of these kind of data representations is that if you look at the output from absolute time, date list, and date string, this is just a number, this is just a list, and this is just a string. That means there is actually up to modern Mathematica 10, there was no real conceptual representation of dates and times in the Wolfram language. And this made things very difficult because these representations here, this looks just like a number. Once it's stored somewhere, there is no more indication that this is actually an elapsed seconds of times, or for example, looks just like a list. And this could be any data, not a date. In computing terms, this means the function return duck type representations, and these duck type representations are difficult to interpret. On top of that, these different representations have no time zone and calendar information. They are always with respect to the local time. So with Mathematica 10, Wolfram completely revised the way dates are represented, and now we have a so-called date object. Date object, if you look at the full form here of this object, this notation here means the full form function is applied to the output of this date object function. And here we clearly see that the date object here contains the date, the time, the elapsed seconds, and the calendar, and even the time zone offset. If you run the date object on a year and a month, then the date object will actually just be a representation of this months in the Gregorian calendar. Of course, we can also use a different time zone, like for example, again, UTC. And again, the resulting date object will record this information that the time zone is UTC. Since this date object also supports different kinds of calendars, for example, we can use the Julian calendar, which is behind us by a few days. Like for example, on the Julian calendar, the actual date is now April 22nd. There's also a representation of times now in Mathematica 10, and this represents a 24-hour clock system in an optional time zone. Just do the time object here, and if we do a full form here, you see that's actually a time object with which records the time here, and which has the type of it is instant. Again, I can select a different time zone here, and if I use the full form here again, you see that the time zone is recorded here as part of the data. Of course, these date objects support the full range of date arithmetic. For example, you have a day range function where we can compute the range of the days from this date to this date, and we only want to return business days. That means the days which fall on a weekend are omitted. And this is actually loaded directly from the Wolfram servers. And here you see, for example, between these two dates, we had the following business days. There's also, for example, a previous date function, which returns the previous date from the current date. And another very important aspect is the conversion from and to ISO date stamps. And here we have the date string function with a time zone, and we use the ISO date time and ISO time zone formats. And this gives you a full ISO date timestamp, which can be recorded, for example, in databases or files. If you want to go the other way around, there is now a resource function, which is called from ISO timestamp, which converts this given timestamp here back to a date object. And this is also loaded from the Wolfram library function repository, and then executes the function in my current session. Once we have a date, we can now think about time series and the way how to represent them in the Wolfram language. One way to do this is to use associations. What are associations? Along with list, associations are a fundamental construct in the Wolfram language. Associations associate keys with values, and they allow very highly efficient lookup and updating, even if there are millions of elements in this association. You might know associations as, for example, as dictionaries in other languages or maps in other languages. And for example, to retrieve some time series, I can use the financial data function built into Mathematica. And let's just look up here Apple stock prices from the beginning of this year. And this method legacy, let's just return the information in a really basic data format, which we can then easily transform. You see, we have here a date list and we have a price. And if I can now very simply using associations red and using the map function, I can now simply transform the given this raw data into a nice association representation of the time list. And you, as you see here, we have now an association where the key is actually the date for the price, and the value is the actual price of the stock. And if we now want to visualize, for example, the prices, we can simply use date list plot. Date list plot gives us a nice representation about the movement of the stock since the beginning of the year. And you see that it's since yesterday it's really fallen quite considerably. We can use functions like, for example, lookup to look up the prices from yesterday and the day before yesterday, and this gives us the prices like 127 and 132. We can use, for example, key select function, which applies to the keys of an association and only select those keys where the actual months of the key is actually April. That's where we can filter all the prices which are valid for the month April. And all the regular mathematical functions operate on values of the association. That means, for example, if I do the mean on this association representation of time series or the standard deviation, it will do the right thing. It will look at all the values there and return the correct result. I can also, for example, apply the moving average function to visualize the moving averages over a period of 3 days. And if I do that, this returns another association, and I can use the date list plot function to show both the Apple prices and the moving average in the same graphics. And here, for example, we have an interesting overlay then of the stock price together with the actual moving average. And another benefit of associations is that you can use a data set to get a browsable representation of the time series. If I do data set here, you see I get a nice representation with a scroll bar, and I can paginate through all this different data. And if you're really dealing with a huge amount of data, this comes in very handy because this actually gives you a manageable representation of the data in your Wolfram session. Once we have an association, let's look at an example how we can do a really useful computation with this kind of association representation of time series. Let's say we want to rank pairs of FANG stocks according to the similarity with respect to their daily returns. What are FANG stocks? FANG stocks are the stocks of these hot NASDAQ noted stocks like Facebook, Apple, Amazon, Google, and Netflix. And these are the tickers here, which NASDAQ uses here. And I can then use the financial data function built into Mathematica to look up the returns, the daily returns for these different stocks. And I'm going to do this for the full last year. And again, I'm using the method legacy in order to return very simple structured data. This gives us the data here shown here, and again, I can then simply use using the table function and association thread and the simple map magic to actually convert this to a list of associations where each element of the list is a time series of the actual returns. Let's just do a visualization then of this data. And here you see with using graphics row, you see that, for example, this daily returns are all the pairs. We can do this using the subset function, and this gives us the pairs we have to consider, like pair 1, 2, 1, 3, and so forth, times 5, 1, 5, and all distinct pairs. And here again, then we can do all the remaining computation can then be done in one step using these pairs here. We look up the daily returns in our list of time series. Then we use the key intersection function. The key intersection will drop all key value pairs that are not present in the given time series, because when you retrieve stock data, some data might be missing, and you only want to operate on data which is present in every time series. And this is exactly what key intersection does. Key intersection drops all key value pairs that are not present in all the given time series. Once we have the common stock prices, we use the values function to look up the actual values in the association, and then finally we simply apply the correlation function to the time series we have looked up here. Finally, then we use the key map function to add the tickers to the output, and then we do a reverse sort because we want to rank the pairs according to the ones which are most similar. And here this is an example. This is the result here, and for example that both Apple and Amazon have those two stocks with the highest correlation in the last year, and the stocks with the lowest correlations are Google and Netflix, although the correlation is still pretty high here. And this, for example, this correlation computation is a very first important step in the computation of many financial models, where you compute, for example, do evaluation of an equity basket. In many cases, you have to do this kind of correlation computations, and with this machinery here, you can do that in Mathematica. Once we have the time series representation, we want to go beyond representation when we want to do computations on these time series. And here Mathematica offers us first-class objects for doing time series computations, and these first-class objects are called time series, event series, and temporal data. What is the difference between these three representations? The first is called time series. It's designed to store a single pass continuous valid time series, and here very important that it's a continuous valid time series. That means when you look up a value which lies in between some given data time series, the value can actually be interpolated by the values which surround the actual timestamp that you look up in your data. Another thing is event series. Event series is designed to store a single pass discrete valued time series, and here we have no interpolation between these different events. And here, for example, if you just think of, for example, things like bird sightings or something, when you are dealing with data where interpolation does not make sense, then you would make use of event series. And then we have temporal data. Temporal data is like a container object to store a number of different time series objects in a single object, and to do operations on the whole set of these different time series which make up the temporal data object. Let's just do a construction here. Here, for example, we have these Apple prices. Let's just relook up what this was. This was just an association where the keys were the dates and the values were the prices. And I can very easily now simply apply the time series function to it, and Mathematica will construct the time series from this data. And here the representation in the notebook gives us some meta information about this time series, like, for example, it's valid from January 4th to May 4th, and it contains 84 data points. It's not regular because the time zeroing is missing the data for the weekends because it's market data. There is no metadata associated with the time series. The output dimension is 1 because we only have one price point. The minimum increment between these times is 1 day. And when you do interpolation between data, Mathematica uses linear interpolation to compute the respective value. We can do the same series same thing with event series. Here, for example, we have similar information given here, but the major difference is that we have no resampling strategy here because event series, as already mentioned, does not do any kinds of interpolation. Here, the FANG daily returns. Let's just for remembering, this was the the list of association, where each association in the list represented the daily returns of the stock from the FANG stocks. And here I can simply also use the temporal data and apply it to my FANG daily returns. And here we have now a temporal data object which comprises a set of time series. We have 5 different paths stored in this temporal data. The output dimension of each path is 1, and the minimum increment is also 86,000 seconds, which corresponds to 1 day. And the resampling value is hold value from left, which is then used upon interpolation. Of course, once we have constructed these time series, there is always the way to unwrap the underlying data. We can use this with the normal function. This will just return the original data we put in. We can do this for time series, event series, and of course also temporal data. And we can, using the standard notation, the standard index notation on this temporal data object, we can look up single values for a certain point in time. Like, for example, if I want in the time series, I want to look up the information for January 8th this year, I can use the sub-value notation, and this will return the price. I can do the same thing for the event series. The interesting thing is time series and event series at a given return a value, while temporal data, which contains 5 paths here in the moment, returns an empirical slice distribution from the given paths. And this data distribution is a first-class representation of a data distribution in the Wolfram language, where I also can do kinds of different computations on this distribution then. If you really want to look up the slice of the data in this temporal data, you can use the slice data property with the data object given here, and this will return the actual value of the returns on January 8th for the different stocks in this temporal data time series object. And for example, we can use on this data distribution, we can apply the mean function to compute the mean of the actual returns from these stocks from a certain date. We can also use the visualization. We can use a datelist plot, for example, to visualize time series. A datelist step plot is very well suited for event time series, and again, a datelist plot can be used to visualize temporal data. Let's just have a look at the resulting graphs. And if you look at this here, we see the stock prices of the Apple stocks. Here for discrete events, we can use a step list plot, which simply draws a step like a graph here. And here, for example, here with the datelist plot plots all the different returns from these 5 paths in a single graph. And the good thing about this high-level representation is that a time series object really holds all the data, and you can work with this data on a very high level and don't have to always consider the small parts that make up the time series. Time series also have properties, and we can look up these properties using the properties string here. And here we see the properties that are available. Most of them are pretty self-explanatory, like, for example, first date, first time, first value, and so on. And for example, in an event series, there are also properties. And for example, if we want to look up the first value in our time series and the last date in our time series and the last time, we can use this, for example, this simple syntax here. And these properties will then be resolved in the following way. We can also apply the underlying data via properties. For example, we can only look up the dates in our time series. This gives us the list of all the dates stored in our time series object. We can look up the times in our date series. Here, the actual times are returned as absolute times. That means as number of seconds elapsed since January 1st, 1900. This is maybe depends on the application, which is more convenient, either returning the dates or the times. Of course, we can also return the values, where these are the actual stock prices here. We can also return both information, both the times and the values in a single information, which is then called the path in the path of our time series. And temporal data has additional plural versions of these properties. Here I'm simply computing the properties, and I'm omitting all the regular time series properties. And here that means a temporal data has these plural properties here. And these plural properties let us, for example, retrieve all the components which are stored in a temporal data object. Here, for example, once we have put in 5 time series into our temporal data object, and here with components we can return these different components as single time series object, where we can do some work on these individual components. Then we can also return, for example, a value list, where this value list contains all the 5 time series values that make up the temporal data. If we want to, for temporal data, if we use the singular properties, we have to specify a time series index. That means, for example, in the temporal data, which has 5 underlying temporal data objects, if we want to use the first value, we have to specify which time series we want to return. In here, we want the second, the third, and the fourth. And if we do that, for example, we get the following information. We can also directly, instead of retrieving all the components in one step, we can also retrieve a certain time series object. Like, for example, here, the fourth time series would be this time series here, which can be then retrieved with the part property. And again, I've already shown it. The slice data returns a slice through all the paths given at a given time in a temporal data object. Let's just do it again here. This is in the slice data from all the different paths at the January 5th this year. And if we do the temporal data for a certain time, we get a data distribution. A great thing about this, so we can also use a list notation to retrieve many dates at the same time. Like, for example, retrieve the slice data for these 3 dates here and render it as a table. And then we get a table where we have for 3 dates we have the actual returns which are contained in our temporal data object. Time series and temporal data interpolate between time series names while event series does not. That means interpolation is done automatically in time series data, which comes in very handy. Let's, for example, evaluate the business day. This is actually was a Saturday or a Sunday. That means it wasn't a business day. And if we look up the event series of our example event series for this date, that means Mathematica will return missing value here because there is no interpolation done for event series objects. On the other hand, if we do the same thing for time series data, time series actually does an interpolation, but it does a linear interpolation by looking at the data in front and at the back of the time I'm looking up. And the same is true for temporal data, where we also do linear interpolation. And how this interpolation is done can be actually queried by using the path function property of a time series. If we look this up for our time series, you see that the time series uses an interpolation function, which is defined in the following way in order to interpolate missing values. If we look up the temporal data function for the path function for temporal data here, you see that it's slightly more complicated here. The interesting thing, if you look the path function for event series, the interesting thing is that it's just a really huge piecewise function, which for each absolute date returns the correct value, and if it doesn't find the value, it simply returns missing here. That means there is no magic is going around. Is going on here. We can always see exactly what is Mathematica is doing here, and we can also always query the function that Mathematica uses internally to compute missing values. If we want to use, for example, order 2 interpolation rather than linear interpolation, we can use upon construction of the time series, we can use the existing time series, construct a new time series from it, and set the resampling method to interpolation with an interpolation order of 2. This will then do a kind of polynomial interpolation. And for example, if we again have to use the business day Q function here and look up the values here, you see that here this is a Friday, this is a Saturday, a Sunday, and a Monday. And if we look up the dates in the time series, you see that the middle 2 dates are actually being interpolated here. And if we look up the same values from our order 2 time series here, you see that the values are actually different because order 2 interpolation uses more information than simple linear interpolation. And depending on the application that you have, you can choose the right interpolation order for your data. Of course, another interesting aspect about time series information is that we can add meta information to our time data, which comes in very handy. Let's just have a look at our temporal data, as already mentioned, has the following components. And we might want to add the information what these components actually are. And we can still have our fan tickers variable, which lists the different stock tickers for these different time series. And we can now really, using the meta information option upon construction of our time series, we can augment the time series data with the actual tickers. And we can also, for example, add a reference date because we looked up the underlying market data today. And if we do that, additional properties are added to the time series information. And you see here in the information here, you see that the metadata lists 2 additional properties. And later, then, when I pass around this temporal data object in my Mathematica session, I can always look up, for example, the underlying tickers by simply applying the tickers property and the reference date property in order to look up the reference date that the market data is valid for. And this comes in really very handy in real-world application because most of the time you need to store some meta information, like, for example, portfolio data or other data that, or some, for example, some other identifiers from market data systems that this data corresponds to, and you can store all this data directly inside the temporal data without having to construct an additional surrounding object which holds this information. Once we have a time series, we can do some basic operations. And again, for example, as you know in Mathematica, there are listable functions which can apply to lists. And these listable functions can automatically thread over values of time series. If we take a look at our data list plot here at the temporal, these were the stock returns here. If we actually want to convert these to actual percent values, we simply multiply the temporal data times 100. And if we do a visualization here, then, for example, we actually see that now the values in the time series have been converted from rates to percent, which lets us do this in a very simple computation. We can also, there's a function which is called time series window, which lets us select a subset of a time series that fall in a given window. For example, if we want to look, let's just have a look up at the time series data again. If we want to look up the data which is valid for February, for the month of February, we say a time series window for our given time series starting from February 1st to February 28th. And if we do that, we get a time series object. And if I do a date list plot here, you see that this time series then simply only contains the selected values. We can convert irregular time series to regular ones. Again, if we look up the time series here, you see that the time series is not regular because, since it's market data, you see here that there is between Friday and Monday, the Saturday and Sunday is missing. That means we don't have regular sampled time series, and the minimum time increment in our time series is 1 day. What we can now do, we can use the time series resample function to transform this irregular regular time series into a regular one. And if we're doing this, you see that the number of data points here increases from 84 to 121, because now Mathematica has resampled the missing data by using the interpolation function. And if we then again query if this time series is regularly sampled and the minimum time increment, you see that it's now a regular time series here. And this is comes in very handy when you clean up initial data so that you have a really regularly shaped time series object. We can use the time series shift function to shift the time series to the left or right. And if we do this, for example, and then do the plot here, for example, I have simply shifted the market data from the Apple stock one month to the future. And this is also for a difference, if you want to apply it, some market data scenarios, this lets you quickly construct a time series from existing market data that you can use for scenario evaluations then. We can use the time series rescale function to rescale a time series in the actual time step in a time series. That means, for example, if I want to compress all the information that is given in this Apple time series in a single month starting today, I can use this time series scale function. And if I do a minimum time increment, then here, then Mathematica has compressed the existing data into a single ones. That means the increment is not 1 day now; it's actually a fraction of a day now. And if I do a time series rescale again and do then a datelist plot together with the existing time series, you see, for example, this was the existing time series here, and here the orange one is the additional data which I said which has been compressed to this in a single month here. Again, this lets you very easily construct for scenario simulations certain market data that you might want to then consider for evaluating some scenarios in a financial application. Of course, time series also allows for applying these functional operations we know from functional programming, like, for example, map, thread, and apply. Everybody knows the map function in Mathematica, and if we have again look up at the time series here, a time series consists of this absolute the absolute time and the values. And if we again use the time series map function, the time series map function is simply applied to the values of the underlying time series. And here we simply wrap the values in a dollar quantity. And if we look up the past, then you see that the actual double values have been augmented with the information that it's actually a currency value in US dollars. This is also something which comes in very handy when doing a cleanup of the data and transforming the data into and augmenting the data with the information that lets you that you then need later upon processing the data. Time series map thread lets us apply a function to both the time series and the values in a time series. Here the actual times are passed as the first argument to this function here, and the values are passed as the second argument. And here, for example, I'm just using this here to construct a new time series, which extracts the value, the month name from the date, and simply uses the same value. And if I do this here, and then look up the path again, you see that I have now a time series where you have the absolute time value, and I have the months together with the actual price here. This is also a very important tool for preparing the data for reports, for example, or augmenting the data with additional information that you can compute from both the key and the value in the time series. If you want to apply a function to values with the same timestamp from multiple different time series, you can use the time series thread function. Let's just have a look at, you can, for example, our temporal data consists of 5 different time series here. And if I can extract these time series here and then use the time series thread function to apply the min-max function to each value in this each slice of value from these different time series objects here. Here, for example, I can simply construct the minimum and the maximum. This gives us another time series object, and if I look at the values then here, you see for each of these 5 different stocks here, I get the minimum return and the maximum return in this time series object here. Again, the important thing is you never have to use loops or any kind of low-level constructs. And by using these thread and map functions, you operate on whole data, and the function take care of doing the right thing. For example, time series thread. If the times of the time series are not equivalent, they are resampled using the union of the times. That means if the time series have, if each of the time series has some omissions because of different holiday calendars, the time series thread function will take care of that and use interpolation to construct the missing data. Of course, another important application of time series is filtering. Here with filtering, we can use the time series aggregate function to, for example, compute the mean of a time series over non-overlapping windows. Here we use a non-overlapping window of 7 days, which means a week. And if we do a date list plot here, we see the actual time series has only 18 points. And here you see the orange curve is the aggregated value, are aggregated values for each month, for each week. We can also use the time series aggregate to do different computations, like, for example, the normality, it computes the mean, but we can also compute the median of non-overlapping windows. And if we do a date list plot here, you see that this here shows the median overlaid with the actual data from the time series. If you want to not use overlapping windows, you can use the moving average function. Here we have a moving average for starting each for a 7-day week. Here again, we plot the resulting list, and you see that this contains many more data points because it's overlapping. Here we see this gives a much more smoother kind of mean value than the one we computed from non-overlapping windows. But of course, we can also moving map. Moving average has a more generalized version, which is called moving map, and moving map can lets us specify the actual computation that we want to use. Here we do it the same again, the same thing for the median. The median for overlapping time varies of the size 7. And if we do a date list plot here, you see the overlapping median from this time series. But of course, Mathematica offers a rich set of different filters which can be applied. For example, you can also use a Gaussian filter with a radius of 4. And here we construct simply a Gaussian filter. And this also gives us a time series. And if we do a date list plot here, you can see the Gaussian filter applied to our time series here. Again, there's a very rich set of filters and helper function that let you work on these time series objects. Now let's move to the most interesting thing that you can do with time series, which is modeling. The Wolfram Language provides a full suite of time series models that you might know from literature. We have moving average models, we have autoregressive models, we have combinations of these autoregressive moving average models. We have autoregressive integrated moving average models, ARMA. Then we have models which consider the seasonality contained in this data. We have even the very modern Garch and Arch models, which are called autoregressive conditional heteroscedastic. I hope I pronounced this correctly. And using the time series model fit functions, we can construct the time series model for time series from an automatically selected model family. Here we have our time series. This is the stock data, and we then use the time series model fit on this data. And here, Mathematica will automatically choose a model that it sees fit, and it also does, for example, here automatic resampling for the missing data. And here it chooses an ARMA model. That means an auto with moving average this time series data. The time series model represents the symbolic time series model obtained from time series model fit. And using the time series forecast function, we can use then to make a k-step ahead forecast beyond the data according to a time series model. For example, here we do a datelist plot with our date time series, and here we use the model that we have to predict the prices, the future prices of Apple stock in the next 2 weeks. And you see here actually the ARMA model gives the orange forecast here, which does not look really like it's a very good forecast. But of course, for market data, it's very difficult for kind of stock. It's difficult to predict future prices from existing models because a lot of information goes into market data, which is simply not covered by previous data in the time series. We can also use an explicit model in the time series model function. Like, for example, let's just say we want to use a more simple model to model our time series. We can use simply a moving average model. And we say time series model fit with a moving average model. This gives us a time series model valid for the moving average family. And if we do a datelist plot here, we see that this looks a little more like it makes some sense. I mean, this may actually happen, but again, for market data, for stock data, predicting the future is really hard. Of course, that means if you put garbage in and you always also get garbage out, it means that the model that you have also always needs to fit the data. And here, for example, I have an example where it's much simpler to find an appropriate model for data. We have a number of airline passengers in thousands from January 1949 to December 1960. This is actually a sample time series which is part of Mathematica. And if we do a datelist plot here, you see this looks very regular, and actually you see that there's some kind of seasonality in this data, which surely can be exploited by an appropriate time series model. And let's just split this data into 2 parts. The first part is the number of airline passengers before 1958, and the other ones is the air passengers since 1958. And here, if you see these 2 data sets here, you see the actual before 1958 and after 1958. Now let's just do a computer time series model from the data before 1958. And Mathematica then uses a ARMA model, which is very interesting because this model, ARMA, is a model which considers seasonality in the model. And we can use then this model to actually forecast the values for 3 more years. And if we do that and do a datelist plot, then you see that the actual forecast is a very good forecast for the actual data here, because the data here is a very good fit for this ARMA model that Mathematica has chosen automatically for the data. And so this is, I mean, you must know your data very well. And of course, you can construct all different time series model explicitly and try to apply this to the data you have. Let's just sum up the workflow that you have with time series. This is some workflow that I usually use when working with time series data. The first step is to import the raw time series data into your Mathematica session. You can do this with an import command, for example, from CVS data or from Excel sheets or from some databases, or you can even retrieve it using built-in Wolfram functions. Then you clean up the raw data. You replace different date and time representations with data objects. You replace missing value placeholders, for example, with the missing symbol, because oftentimes data you get from Excel sheet or something has a certain value, missing value, like for example, -20 is used for missing value, and you can then use rules to replace this with the missing symbol. Once you have then you convert the cleaned up raw data to a list of associations or a multiple list of associations. You can then do application-specific transformation on this association data. You can then convert this associations to a data set for simple computations. You can invert the associations to time series, temporal data, or event series where appropriate. And you can use time series model fit and time series model forecast to do modeling and forecasting of the data. Here I've collected some additional online resources, which you can then inspect later once I have published this notebook. All the attendees of this talk will, of course, receive a link to the presentation. And there I've also listed some additional resources in the Wolfram resources repository. And there's another interesting talk on YouTube which gives you more information on time series. And we are almost done. So thank you for your attention. And are there any questions on time series data with Mathematica?